And thank you again for being here. We're going to continue with our Andy Talks. Jay Whitacre is Professor of Material Science and Engineering and Public Policy. Received a bachelor's degree at Oberlin and a PhD at Michigan. In addition to his professorial duties here, he's the founder of the local company Aqueous Energy. And among his many awards and prizes, he received the 2015 Lemelson Prize, often considered to be the highest award an inventor can receive. Today, he's talking about making robust next-generation energy storage, the why and how of batteries that last decades. Jay Whitacre.
Thank you so much, Jerry. Can everyone hear me okay? Yes. Great. So it's a real honor to be here. It's super exciting to watch I was here in the early days, the groundbreaking for the Scott Institute. Now the building is open, and now we're having sort of our first real week-long event, and it's great to be part of it. So I thank the organizers for the invitation, and I'm happy to talk. And this talk today is more about what's going on in general, CMU energy storage, and a little bit less. How do I get out of this? How do I go to my talk? Sorry about that. There we go. Great, and more about energy storage research that's going on, of which I am a part of, and we are trying to answer some important questions. So energy storage is the answer. We hear this a lot. It's bandied about for transportation. It's bandied about for stationary applications. Several folks have already touched on it today in their analysis, be it for renewables or for transportation already. But I kind of want to go the other direction. What's the question that we're trying to answer here in the first place? Is there an easy way for us to characterize what we're trying to do by first thinking about what we would do before we already look at the answer at the beginning? So transportation, the question really is, how can we enable electrified motion of people and cargo and whatnot around? And this is sort of the very elegant Tesla Model S. This is the inside of the Model S. It has this beautiful sort of chassis, and on the bottom of this chassis are about 8,000, about double A size lithium-ion batteries. It gives enough range for people to buy it, and it is a remarkable piece of technology. And so it has been enabled. This question is somewhat answered. Maybe not economically for everybody, but it does exist as a solution. And for stationary use, the question is a little bit different. It's not a matter necessarily of enabling. It's how can we level out intermittent renewables? And this is what Jay App talked about just moments ago, and a little bit Inej as well. And again, we've got this really jagged power supplies. And those of you who are newbies to energy data, this is power, this is time, this is the change in power out of a solar PV array over time. Some days it's very crisp, very, very clean, there's no clouds. Other days it's quite jagged. And again, we've already seen if you can aggregate these, they have different signatures than if you just go on location. And likewise, wind is all over the place as well. So if we can figure out a way to buffer this with the load that's nearby, which is different than this, with some other thing, a battery, or an energy storage solution of some ways, you could, in theory, use lots of this, right? It's sort of intuitively makes sense. Of course, a lot of deeper analysis shows you don't need many batteries, and you can't probably get rid of all carbon sources, but maybe there's a best hybrid solution. And I guess what I'm really here to ask then is we sort of know what the answers and questions are for these two cases, but now what's the real key technical questions of what has worked and what we need to do to make this work even better for the future? And there really is one technical answer that makes great sense, at least for stationary storage. I already showed you the transportation one. It works, but it's economically sort of dicey, right? The battery pack for a Tesla Model S is still quite pricey, and it's not exactly clear how it gets down so that we can have $25,000, $30,000 vehicles that are profitable for a car company and have enough range for a consumer. But there is one answer that makes sense. Pumped hydro. Pumped hydro storage has been around for over 100 years, and the resource that it makes use of is a change in altitude. This is a river, and this is a reservoir that's been built above a river, and this is probably hundreds of feet of vertical change. And it's a very simple concept. When you are not using electricity, or when you have electricity that's extra, you use it to pump water up that hill, and you put it inside the reservoir. And when you need extra electricity, you simply turn on a turbine that's down here, and you extract electricity from the gravity that you input when you put the water up high. And this is actually significantly more common than you might imagine. This is actually everywhere. And I'll talk about the preponderance in a second. But why does it work? And it works basically because we're talking about business here. It's business sense. Concept number one is that electrons and dollars are fungible in the energy business. Most people, when they buy or sell energy, don't particularly account for where it came from or how it was handled or how efficient it was. They just simply want to know what the price is, and that price determines its amount of use. So it's very simple economics in some ways. So it's a business, and so we treat this as a business. We look at the capital expenditure of the device. We look at its round-trip energy efficiency. The more efficiency, the more we lose to heat in terms of lower efficiency, the more we have to make up in some other metric. And the other key one is the ability to process energy over time. And that not over hours or days, but decades or multiple decades. The more watt hours a storage device can process, the higher capital expenditure and lower efficiency you can justify. So there's this tension between spending a lot for something that lasts a very long time or spending much less for something that you have to replace frequently. And that trade-off exists in all energy storage applications. In pumped hydro, for example, capital expenditure can be extraordinarily high. The picture I just showed you had what was a valley above a river that had been dammed off and structurally reworked. They had to put all this plumbing in. They had to install these turbines. Very expensive. So that's high. The energy efficiency for pumped hydro is not great. 70s to 80% on a very good day. And that's because there's all these mechanical losses to moving water around that. And there's also some evaporation of the water when it's up high, right? You put it in this sort of reservoir and it's open to the air. You will actually lose some of the stored water just in terms of transevaporation. Of course, rain goes the other way, so it depends on where you are. But the ability to process watt hours over time is extraordinarily high for pumped hydro. Decades and decades and decades. I mean, once you set something up, it will essentially run forever. Forever being, I don't know how many decades, but a very long time. I went to Hoover Dam last year. It's still running, and it is essentially a pumped hydro facility. And you would have to put a pump back up into the backside of Hoover, but it still is running, and this was a World War II era project. So when you can amortize that capital over that many years, then it starts to make sense from a business perspective, and that's where we are with the pumped hydro in the world right now. And there's over 100 gigawatts of pumped hydro installed everywhere. And there's about 20% of that is in North America. And if you think that this is maybe between 5 and 10 hours, or maybe even much longer in some cases of storage, we're talking about terawatt-hour class energy storage already plugged into the grid and doing sort of very valid and important exercises already. So that's one of the answers. This exists, and the price point for this is under 10 cents a kilowatt hour stored, delivered, lifetime cost to store electricity. That metric really matters. And so this also sets the bar for any other storage technology that you want to be relevant. If you can't get to this kind of functionality, you're not going to be able to have this level of impact. Now, there's a problem with pumped hydro. Obviously, it's very location specific. If you don't have this resource in the form of a very large vertical change with the right terrain and the right local policies amenable to reworking the environment, you can't install it. And in fact, many analyses show that there probably is not too many more places around the developed world where you can do this without causing some serious issues. So we're kind of tapped out with that. And so the question now is, what's the next thing we're going to be looking at? So other energy storage technologies. And I'm going to limit the comments that I have about these to things that are going to be relevant maybe in the next 10 or 15 years. There are many things that could be sort of the next thing, right? And there's great work going on around those, but they're so nascent that it's hard to even understand what the limitations might be and the challenges are. So we have a pretty good idea of some things that are happening right now, and that's kind of what we're working on here at CMU, and I want to talk a little bit about those three aspects of that. So thing one about this kind of storage technology is that in many ways, the things that are on the market right now are costed down. When I say that, I mean that they sort of have already been through a learning curve. They're manufactured, and there's not a huge, obvious way to cut the price in half again, the sales price in half again in these technologies. They're mature. And some of them are just coming onto the market. I have a product with spin-off company Aqueous. We're just putting it out there. It will cost down, but it's not clear that it's going to cost down all the way to a third of what we are selling right now, right? So there's some limits to anything that's sort of productized or nearly productized. So maybe trying to figure out just a low-cost solution, given what we have in the next 10 years, is not the right way to go. And many of them are already as efficient as possible. A good lithium-ion battery or a good lead-acid battery will be in the 90% round-trip efficiency or better. That's actually quite reasonable. And if you have, and it depends entirely on how you size the battery and how you design it and what sort of use case it is, but you can really get decent efficiencies if you're careful. But it's the limited lifetimes, I think, that really matter right now for this next ilk of energy storage technologies. Why are they limited? Many of them are electrochemical in nature, and this means that they have some kind of chemical reactions occurring within their electrodes, and these are often just inherently degrading. Like there's almost no situation where you could say you have something going through chemical reactions routinely on a daily basis, sometimes at elevated temperatures for decades, where there's not some loss in function. And so understanding how to overcome and fixing this aspect might be the thing to approach the best, because we still are learning an awful lot about the degradation and loss of function of electrochemical reactions in the materials inside these batteries. And if we can fix that, you don't have to change the rest of the battery. You can implement materials improvements, maybe at this fundamental level, and increase the lifetime, get to the decades you need to amortize out the cost to get to the business case that makes sense for storage. Okay? So now I've got sort of three little vignettes of sort of research that's going on here at Carnegie Mellon that I thought would be kind of fun to show you guys. Story number one are the cells that are being used essentially in the Tesla pack. And here's a picture of one. It's a AA size thing. It's called an 18650. And interestingly, you might be surprised to know, you might think that if you buy an $85,000 or $90,000 vehicle, sometimes more, that the battery in it would be able to go many thousands of deep discharge cycles. Not true. The cells in the Tesla actually are only designed or only sort of spec'd or warrantied out to somewhere between 500 and 1,000 deep discharge cycles. And you might think, well, that doesn't seem like very much. But then you realize that each cycle represents between 200 and 250 miles. And if you do 500 of those, you're at 125,000 miles traveled, which is not an unreasonable amount to expect a vehicle, a first ownership vehicle to go. So maybe it makes sense. And then it's augmented by the idea that if you shallowly cycle these batteries, they actually last longer than this 500 cycle count. But that being said, wouldn't it be great if, and what these guys don't show you is that somewhere out here there's like a real lip down. It doesn't just keep on going. In many cases, there's a real loss in function out here. And wouldn't it be great if that didn't happen, if we can figure out how to make these keep going and maybe implement these more broadly. And so one of the things that we're looking at here at CMU is understanding sort of why this failure is happening. And one of the most common things we all think about in the battery research community is the formation of a film on the anode side called a surface electrode interface, an SEI layer. And this is a pristine harvested electrode from one of those batteries. And it's a graphite system, and you can see these nice graphite flakes. It's very clean. And this is after 600 or 700 cycles at elevated temperature. You've seen it's all got coated up with this gunk. And this is largely a combination of lithium carbonate and lithium fluoride and lithium hydroxides that sort of gunk up, and they actually disallow the transport of the ions that want to get inside the electrode, and they stop it up. And this is a plan view scanning electron micrograph. So we're looking onto the surface of this electrode, and we're trying to understand, well, what's happening? Is it just getting gummed up from the top or not? But we have another way to look at this, and this actually is in collaboration with Sean Lister and his research group. This is a Nano X-ray Tomography image, and it's a three-dimensional rendering where you can actually use the same kind of X-ray CT that you might be familiar with from a medical perspective. You can do it with nano resolution on these very lightweight electrodes. This is a carbon system, so it's very difficult to get this resolution and this imagery correctly. This is actually an extraordinary image. We can see all these different graphitic flakes in here. You can see a tremendous amount of detail, and these white dots are really representative of buildups of some sort or another. And we are using this data to understand now not just what happens on the surface of the electrodes, but what's happening on the inside, and how to back calculate the formation of the SEI as it grows and ceases to function in the battery. So why is this important? We can take this data to understand and design new electrode structures that will facilitate better long-term performance. We can look at the performance of different electrolyte additives that could greatly increase the lifetime of the battery. And we could also look at different charge control methodologies. There's a lot of great work out there talking about how, depending on how you charge these batteries, you may reduce the formation of this pernicious layer that eventually causes death in the battery. So that's story one. Story two is near and dear to my heart. These are aqueous electrolyte batteries. This was the, not this technology, but this concept of a low-cost saltwater-based battery was what became Aqueon and came out of CMU years ago. And now we're trying to look at the next generation of materials, and we're trying to look very aggressively at how to make materials that are completely stable in that kind of environment. One of the things that we do is we create model systems. This is a model system of an anode material. This is sodium dititanium triphosphate. It's a mouthful, but what for this audience matters is that I can make really nice, almost perfect cubes of this material. And why I like the perfect cubes is that it gives me very flat facets and corners. So we have a really good sense of the uniformity and what this should look like if nothing goes wrong with it. And then I see that if I expose it to the wrong environment, and this is an extreme voltage, extreme pH environment, it collapses. We lose the structure. So if I expose it to the wrong use conditions, it will collapse and lose its ability to store energy the way I want it to. It should always look like this. Now, the good thing about water is that there's no SEI formation, so I can get away from that. The bad thing about water is that it often corrodes, especially at negative potentials, any kind of system that I might want to use. So we're trying to understand what other things we might do to protect this material, our precious functional material, from the water-like environment that can cause corrosion. One of the projects is to use functional, electronically and ionically functional polymers to coat these cubes such that when they're used, they don't actually come in contact with the corrosive environment. In this case, it's a polypyrrole material. And these are two different thicknesses. In this case, it's quite thick. In this case, it's very thin. Turns out there's a Goldilocks thing where if you're too thick, you don't get very good performance. If you're too thin, you will actually not protect the material. But if you get it just right, you can dramatically improve the long-term performance of this material. Now, this is a very aggressive, high-temperature, sort of dwell at abuse conditions test. So if we don't improve it at all, we lose almost all the capacity in 50 of these sort of test cycles. But we get a substantial improvement if we coat with this material. So just an example, how we look at things to make them better. And again, we're trying to make going from days of use, years of use, to decades, multiple decades of use to justify the expense that's inherent with this kind of technology. Thing three, and this is sort of a new project that's going on. We have a team of folks here at the Scott Institute that are looking to understand how to figure out how to sort of make stable and make better storage technologies that are enabled by reactions at surfaces. These reactions at surfaces could be at the kind of sort of cube level that I just showed you, or they could be catalysts in things that are batteries or fuel cell-like systems. There's a thing called a flow battery. There's another thing called a lithium-air battery, both of which are very promising in some ways, but they may have this pernicious long-term electrochemical stability issue that we want to focus on. And so we're now in the process of selecting model systems and ideas to come up with what's next. And the campuses, again, is on extending life and improving efficiency. And so I've got one more picture here. And Venkat, who's another professor in mechanical engineering, he's a specialist in this technology, lithium-air batteries. And if you look at this, and I won't belabor it, but you've got this pool of metallic lithium as an anode. Metallic lithium would be a great way to store energy. It's lightweight. It's incredibly energy dense. It's not that expensive. It's pretty abundant. But you have to move this lithium through a couple different electrolyte layers, and then it has to have a reaction with some things that happen with air. And so oxygen comes in, and you have to convert air oxygen into some solution-based ion that will go in and interact with the lithium somehow. And that reaction has to take place on some surface. And typically people have been using carbon surfaces to enable this, but long-term studies on the stability of those carbon surfaces show that they're not fully stable. Right? We're losing a little bit of carbon. Carbon monoxide, carbon dioxide will come out of the system along with the other breathable reactants and products that go in and out of the system. And at the end of the day, we're going to have to figure out what other catalysts might enable this. So there's a slew of potential low-cost systems and ways of putting these electrodes together that we can leverage with all the existing talent we have here. And so it's really exciting to be part of this new effort to understand and how to extend and make all this better. Sorry. So take-home messages. You're going to see a lot of these quick talks today, and I can't imagine anyone remembering everything. So a couple of things. Near-term energy storage solutions are not going to be all that meaningfully less expensive to manufacture. We've already sort of gotten there. So what we have to do is we have to increase lifetime. We have to increase lifetime to the extent that we're at the duration that you would expect from a pumped hydro station, so it lasts a very, very long time. And we're working on it here at CMU. We're trying to move the bar to get to the right price point, to hit the economics so that we can say this is a business case. This will make sense for more than just a laboratory demonstration. And so hopefully between now and 10 years from now, we'll have some amazing things coming out of here. And I thank you for your time.